Using different compounding frequencies with the same advertised annual interest rate can produce much differing results. For example, let's imagine we start with $1, just to make our calculations simple, and to keep them simple, an annual interest rate of 100%. But we're going to look at what happens to the balance after 1 year using different compounding frequencies. So we plug in 1 for the principal, 1 representing 100% for the annual rate, and 1 for the number of years that have passed. And so that formula is going to depend on the compounding frequency m. Let's take a look at what happens to the balance over different compounding frequencies. Let's start with semi-annually. So that means we're compounding twice per year. If we plug a 2 in for both values of m and evaluate that on a calculator, we get a decimal of 2.25. Now let's go quarterly, and we end up with a different balance at the end. Why is that? Well, when we compounded quarterly, the first time we gave interest was after 3 months. The second time was after 6 months. So after 6 months, the balance was already bigger than it would have been if we hadn't given any interest, because we gave some interest after 3 months. So that means we were calculating interest on a larger balance, and that's how we ended up with a greater value than we did when the first time we calculated interest was at 6 months. And this pattern continues. If we compound monthly 12 times per year, the balance at the end of a year will be even larger. If we compound daily, the balance will be even larger. And now it's tempting to ask, well, could I make the balance really, really big? Like, could I make the balance $1 million if I just compound really, really fast? So if you continue to look at this pattern, maybe you compound every hour or every second, and yeah, the numbers are getting bigger, but not much bigger. In fact, they're closing in on a number that looks kind of familiar. I actually rounded up to get this value, 2.71828, and that number we should recognize as E, that special number that shows up a lot in calculus especially. It's approximately, it's not exactly, but it's approximately 2.71828. And the faster we compound interest in the previous example, the closer the balance got to this number after 1 year. So that actually turns out to be the best we could ever do. No matter how fast we compound 100% interest for 1 year, we'll never end up with more than E dollars at the end of the year. In general, it turns out we can do the same sort of calculation for any interest rate, for any number of years, and although we're not going to go through an entire derivation, it comes out to be a formula involving E. You take the amount you start with and multiply it by e to the RT, and that gives you the best possible balance, the most money you could end up with compounding faster and faster and faster. It's almost as if you're compounding every single instant of time. And for that reason, this is called continuous compounding. And if you look at this formula, this gives you the exact answer we got on the previous slide. If you plug in a 1 for each of these values, you get 1 times e to the 1, which is E. So this is a formula we can use to calculate continuous compounding. There's no such thing as continuous compounding. A bank computer cannot actually apply interest every single instant of time that passes. But this continuous compounding formula gives us a good way of estimating the actual balance when you're compounding fairly frequently. For example, daily, as many banks do. To see that, let's look at an example. Imagine we start with $500 in an account that earns 4% annual interest. Let's see what happens if we use the compound interest formula for daily compounding and compare that with the formula we just deduced for continuous compounding. And we'll use them both over a period of 5 years. So, to do the daily calculation, we plug in, this is supposed to be 365 in this denominator. And calculating that gives you $610.69 at the end of 5 years. Whereas if we do it continuously, plug the interest rate and the principal into the continuous compounding formula from the previous slide, and 5 for the number of years, you end up with $610.70. Almost the same thing. You're off by 1 penny. So again, if you're looking at this slide, this denominator should be 365. So using the exact formula for daily compounding versus this formula for continuous compounding gives you a pretty good estimate from the continuous compounding formula. And for the purposes of what we're doing now, there's probably no need to use the continuous compounding estimate. On the other hand, in calculus, as we've discussed before, it's really easier to work with exponential functions that have a base of e, and so that's one reason why you might want to use the continuous compounding formulas instead if you have to do something more complicated with it, like you will in calculus.